Hey everyone, and welcome back. In our last explainer, we talked all about the precision loss problem that comes with floating point numbers. Well, today, things get even weirder. We're going to watch a number literally vanish into thin air. This is a phenomenon called floating point absorption, and it's where adding two numbers together can actually make one of them disappear completely. Let's see how it works.
So we're going to start with a paradox, a moment where what you learned in math class seems to totally disagree with how a computer actually gets the job done. Take a look at this. It's kind of mind-bending. On the left, it's just simple math, right? 1 million plus a tiny little fraction equals a slightly bigger number. But on the right, you see the computer's reality. 1 million plus that same fraction equals 1 million. The smaller number isn't rounded, it's just gone. Poof! So how on earth is that possible? This isn't just rounding, folks. This is a straight-up vanishing act.
Okay, to figure this out, you have to get one thing straight. The computer isn't breaking the rules of math. Not at all. It's just, well, it's playing by its own set of very strict, very mechanical rules. And there are two big ones we need to know about. First up, we have the rule of alignment. See, a computer just can't add numbers that are on totally different scales or have different exponents. You can't just match them together. It's kind of like trying to get two gears of completely different sizes to mesh. It's just not going to work, right? So before it can even think about adding, the hardware has to force the smaller number's scale to match the bigger one. And rule number two is the container. A floating point number doesn't get unlimited space to exist. Nope, it's got this little fixed size tray to hold all its important digits. Now, to make this super clear, we're going to pretend our computer only has room for 4 digits. And here's the really important part. If a digit gets pushed past that last little box, it's not rounded down, it just falls off into the void. It's gone. It ceases to exist for the computer.
And that little tray, that container, it's got a proper name, the Mantissa. That's the part of the number that holds all the good stuff, all the precision. And, as you're about to see, its limited size is the key to this whole disappearing act. All right, so now we know the rules of the game. You gotta align the numbers, and the box you put them in is only so big. Let's watch this magic trick in slow motion and see exactly where our little number disappears. Okay, here's our setup. We're trying to add 1,000 and 0.5. The big number, 1,000, we'll call that our anchor. In scientific notation, that's 1.000 times 10 to the power of 3. And our little number, 0.5, that's our victim. That's 5.0 times 10 to the power of -1. You see the problem already, right? They're exponents, 3 and -1. They just don't match. And the computer has to fix that.
So to get those exponents aligned, the computer starts shoving the decimal point of our victim number. And for every single step that exponent has to climb to match the anchor's exponent of 3, that important little digit, the 5, gets pushed one slot further to the right inside its container.
And here we are. After a couple of shifts, our 5 is sitting right at the very edge in the last box of our little 4-box container. The data's still there, it's safe for now, but that tray is totally full. And here's the kicker. We still need to do one more shift to get that exponent up to 3. And this is the moment it all happens. That final shift for alignment takes place. But there's no more room in the Mantissa. The digit 5 gets pushed right off the edge into the drop-off zone. It didn't get rounded, it was just discarded. It's completely gone.
So, with the victim number's only significant digit totally lost, the computer can finally do the addition. But what? What's actually left to add? Nothing. 0. So the computer perfectly and without error adds 1,000 to 0, and the answer is 1,000. The 0.5 wasn't a rounding error. It was completely lost during that mechanical alignment process. Okay, so that was our little 4-box simulation. Obviously, a real computer is a bit more powerful than that, so let's scale this up and talk about why this actually matters in the real world.
Right, so a real computer using a standard 32-bit float doesn't have 4 boxes. It gives you 23 bits for that Mantissa. That's a lot more room, for sure. But the logic, it's exactly the same. If the difference in scale between the two numbers you're adding is big enough, the smaller number's bits are still going to get shifted all the way off the right side and just vanish.
So why should you care about this? I mean, this isn't just some weird theoretical quirk. It has real, tangible, and honestly, often frustrating consequences in things like physics engines and computer graphics. One of the classic examples is something called the frozen object problem. Imagine you're in a video game and an object is really, really far away from the center of the world. Its position is a huge number. Now, what happens if it tries to move just a tiny bit? You're adding a very small velocity number to that gigantic position number. And the result? Well, you guessed it. That small velocity value gets completely absorbed. The position update becomes 0, and the object just freezes in place.
Okay, let's do a quick recap. What are the key things we've learned about this vanishing act?
It really all boils down to this. 1. Computers have limited precision, that fixed-size tray called the Mantissa. 2. To add numbers, the hardware has to align their exponents, and that forces the smaller number to shift its digits. 3. If that shift is too big, the data literally falls off the edge. That's absorption. And 4. The consequence is that small but really important changes, like an object's velocity, can get completely and utterly ignored. And that really is the main idea you should walk away with. The quote says it all. The small number did not round down. It vanished entirely due to precision limits. So the crucial point is that the computer isn't making a math error. It's perfectly following mechanical rules that just happen to lead to information loss. In the next explainer, we'll explore the architecture of floating point, where we will discover what truly matters. Stay tuned.